Okay, hopefully this one will be shorter. And hopefully it'll capture audio adequately without having to redo it 3 times. So this is my, hang on, I don't know how to pause this thing, got a clear throat. YouTuber I'm not. Welcome to the amazing N8NK Unitz electronic numerical calculator. What I use this spreadsheet for is basic Ohms Law calculation, as you'll see here in this first section. Might sound silly, but I've always, when I'm working on something, both spreadsheets are running. I've got a 4 workspace desktop, and I just toggle between them as need be. So anyway, basic Ohms Law calculation. Next section, basic Ohms Law calculations that use squares and root functions. Typically combining your power formula with your classic Ohms Law formula, P, IE, and EIR, combines the two. Can be very handy. And again, you can use them, you can find the converters on the web, but why? When I got this running on my desktop almost always. So that's what that section does. Next section, unit conversion. I won't run through the list. You can look and see. Very handy. Very, very handy, as a matter of fact. Next section, miscellaneous RF output calculations. These first 3 are handy for calculating power out, whether you've got a voltage measurement in RMS or peak to peak. This one being particularly handy when using an oscilloscope and taking measurements in a circuit. I don't really need to go through them all. This one will calculate peak to peak voltage given load resistance and power output. This one will calculate my load impedance, my load resistance, if you will, in an output collector, in an output stage using a bipolar NPN transistor, because it takes into account the base to emitter voltage drop. That's why I wrote that section into it. Decibel calculations. Boy, can this be handy. Fun to play with too. If you've got a 100-watt radio and I've got a 5-watt radio, how many dB are you up on me by? 13. You've got me by 2 S units and a decibel. If you've got a kilowatt, now then you've got me by 23 dB. You've almost got me by 4 S units. You know what though? But if you're at 10 dB over S9, now you've got me at S9 minus 30 dB below S9. I'd be S4, you know. I think I said that right. You get the drift. But power ratios to dB. Same thing for voltage or current ratios, because I use a log 10 function, not a log 20 function. So power is different than voltage and current. Same calculation, but different. Same but different. Power 2 from power 1 in dB. I'll show you what this can be useful for. If I've got, I don't know, if I've got a 2-watt preamp, 2-watt driver stage in a transmitter I'm designing, and I want a little more power output, I look around, I see that I can easily get another 8 dB with a IRFZ 510 MOSFET by adding like 3 or 4 parts. I can achieve 12 watts. That's an example of where you might use something. It's actually used for a lot, actually. Anyway, that's dB calculations. Next section, dBm calculations. Power to dBm, peak to dBm. I'll give you an example of where this is useful for. The last transceiver I designed and prototyped, I needed a local oscillator output that would provide a minimum of minus 25 dBm to the input of the Gilbert cell mixer chip. So I needed minus 25 dBm or better. I've heard that 200 millivolts would achieve that. 200 millivolts, the input impedance of the mixer chip is 1500 ohms. Ohms? Wait, what did I do? Oh my god. I screwed up. Okay, 200 millivolts peak to peak, 1500 ohms on the input to that mixer chip. Minus 24 dBm, that is just a tad bit above the minus 25 dBm ideal injection level. I went for 250 millivolts and injected minus 22.8 dBm. That's an example of where that can be useful. I had a bunch of examples in mind to show people, to show my brother man art, but I'm nervous and I can't remember. I can't remember. 1 watt should be 1000 dBm. I mean, should be 1000 milliwatts, which is 30 dBm. Anyway, two caps or two resistors. Might sound silly, but if you need an off-standard value resistor or cap, and all you got is your junk box, this might save you. You know. Really might. I don't need a 4.7K in parallel with 6.8K. You know, it's actually very handy. And I'll give you an example. Okay. I'm working on an antique All-American 5 tube type radio, and the oscillator pattern on the tuning condenser can't quite tune high enough. It's too high in value. Let's say that it's a 300 picofarad section on that cap. I'd like to drop it down a little bit, but what value cap to put in series with it to drop it down a little? Well, I'll try 10,000 picofarads, which is what, 10 nanofarads? And it just so happens that wouldn't be a bad value, actually, you know. So that's where that could come in handy, and does come in handy. Another temperature conversion, just cause sometimes people ask me, and I might be talking to a European and he asks what the temperature here is, and all I know is that it's 48 degrees outside. You know? Nope, wrong box. So I restore antique radios from from time to time, and that's why I wrote this section in to the spreadsheet. Resistor tolerance range calculate. What if I'm working on a VTVM, which I was, and it had 5% tolerance resistors on the band switch, which it did, and it had a strange value resistor, like 8.73K. Now I can put a value in K here, and the result will be in K. So if it calls for a 5% tolerance at 8.73K, all I got to do is type it in, look at this, and look at my meter, and I'll know real quick and real easy without doing any mental math whether that resistor falls within range. So I put in 8.73K. I could have put in 8730. It's the same thing. Same thing. If you input a value of ohms, the output's in ohms. God, I know there is more I wanted to mention here. Oh, I know. You want to see a fun one? Here's a fun example. I wonder what the peak-to-peak voltage is on my unun. Okay, my 80 meter end-fed half wave. I find that I get a perfect match using the 81-to-1 tap. The primary is 50 ohms times 81. That's 4,050 ohms. Okay. So E equals the square root of PR. Okay. What if I'm running 5 watts? And what's the voltage on the antenna terminal of the unun? My union, 4,050 ohms. Using 5 watts, 142 volts. But that's in RMS. I'm going to copy that. You want to see what the peak-to-peak voltage is? We'll use the converter down here. RMS to peak-to-peak. My RMS was 142 volts. Using QRP, you touch the antenna terminal on that unun, and you're touching 402 volts. The next section, miscellaneous RF output calculations. I use this, like I said, see what we did up above here. We converted power and impedance to RMS voltage, converted RMS voltage to peak voltage. I can do that in one whack here. RL, my load resistance 40 to 50, my power is 5 watts, and you'll see that I've got the same result, 402 volts. Peak to peak at 5 watts. What's the voltage at 100 watts? 1.8 kilovolts. Yeah, now I'm thinking I better check my voltage rating of the cap on my unun if I'm going to run. It's not 1.8 kilovolts. I think it's a 1600 volt cap. It hasn't broke down yet, but it will if I give it time. What about if you run 1,000 watts? What if you run 1,500 watts RMS? What kind of peak voltage will you see on your antenna terminal? Let's call it 7,000 volts. Let's go back to QRP. Okay, so on the antenna terminal of the unun, we've got 402 volts, right? What kind of voltage should we see at the input? Our 50 ohm coaxial input? 44 volts, peak to peak. Will you feel it? Yup. Yep, it'll give you a little owie, but just a little one. So anyway, that's basically the rundown of the amazing N8NK Unitz electronic numerical calculator.